2015 to October 2015. His research interests include 3D printing and additive manufacturing, CAD/CAM architectures, command generation, FPGA-based EMT systems, and computational geometry for design and manufacturing. Yes, Dr. Yaman, we are listening to you.
Thank you very much for the introduction. Me, Ulaş Yaman, and Professor Mekla is here in the Smart Manufacturing Lab right now. And you can see behind us the hybrid platform. And the name of the project was a Smart and Hybrid Manufacturing System, which utilizes additive and subtractive type of operations on the same platform. And this project was funded by TÜBİTAK. And we have our scholars, our PhD students here, as you see. Now I will start giving you details about this machine platform, actually manufacturing platform. Let me quickly go through the outline. I will give you a brief history, how we started working on this project, what was our main motivation, and then give you the main properties of different parts of our system, discuss some novel features of our platform, and then focus a bit more on the main novelty, maybe, which is where I will be with in fused filament fabrication manufacturing process, and then discuss the fundamentals of additive manufacturing side of our system, then give brief information about the machining side, and discuss some short-term revisions, what we are planning to do in the 3 months, and then I will also give you some information about our feature studies, and lastly I will give some remarks and conclude my presentation. Yes, how we start, actually we start discussing some hybrid platforms, and our main initial goal actually was to develop some smart algorithms for path planning in hybrid systems. And then we searched for some products. There were some polymer-based products, but they were not a complete hybrid platform. What they were doing is change the extruder heads of an different fabrication method, and then mount a spindle for the machining, and then do the machining operation later. But this wasn't actually what we were looking for, and then that's why we start thinking about designing a new hybrid platform based on polymers, doing some extrusion mainly, and then later doing some machining or doing these 2 manufacturing processes at the same time. And then we start writing a grant. Hopefully we got the grant from TÜBİTAK in November 2017, and then we started working on some different designs. We had many designs, about maybe 10 of them. We had multi-axis. By the way, I forgot to say that our platform is multi-axis. We have 5 + 1 + 1 axis. I will give you the details. And in our alternative designs, we also worked on multi-axis hybrid solutions. In some of them, we have the rotational axis on the extruder head or the milling head, but later we changed our mind, and right now we have the rotational axis on the main table. And we start doing some manufacturing to the end of 2018, and we start focusing on some details. We manufacture linear stages, linear axis, and then rotary stages. And we focused on some electronics part of the project, and we performed some initial tasks on the stages. And we try to see the maximum speed. We try to see the repeatability. We try to see the resolution of these stages. And then we got the extruder heads working around March of 2020, this year. And then unfortunately we had this pandemic, and we had a kind of a break, maybe for about 3 to 4 months. And then we start working on the project again. And we have the machining heads running around July. And then we have our first printing test again in summer, first machining test, and lastly we have done some improvements, some updates last month. And now it's ready. We can do manufacturing with machining operations or with extrusion or piece level fabrication type of additive manufacturing methods. And on the other hand, we can also use them at the same time. That's one of the main properties of our system. This is a hybrid platform. We can use all these manufacturing processes in the same machine. So now let me focus on some details. This is our close-up view of our system. You can see the same one behind us. And as I mentioned at the beginning, we have 5 plus 1 plus 1 axis. So what are these numbers? First of all, 5 means actually X, Y, Z, B, and C. You can consider this side as machine side, and this side can be considered as additive manufacturing side. In addition to these 5 axes, X, Y, Z, B, and C, we have 2 more axes. What are they? First one is an independent vertical motion. This is called as W, and as you see, our extruder head is mounted onto that W axis, and it can independently move with respect to the Z axis. So it gives you lots of freedom. And then we have 2 rotational, this corresponds to 2 axes in this 5, and rotation around Z axis is C obviously, and rotation around Y axis is called V. And if you forget about this additive manufacturing side, you can also use this part as a 5-axis CNC machine. Right now, we didn't actually try it on aluminum or some type of steel, but in upcoming months, first we want to try it on aluminum and then maybe some mild steels. We need to have some time. And we have 1 more additional axis. This is Q axis, as you see here. If you are familiar with piece level fabrication methods, actually you don't need to rotate the nozzle. But I will give you details in a moment. Since in order to use our concept, we need to have a rotating extruder. So that's why we have a +1 here. Let me show you some videos of our systems. Actually, axes, these are the linear axes. And we actually recorded them maybe about a year ago. And as you see now, the rotational axis one, here just X and Y axis are moving. And you can see how flexible it is. If you don't want to have 5-axis platform, then you can remove the rotational platforms and use your system as a 3-axis machining system or 3-axis type of conventional type of desktop printers. And we were trying to find actually maximum speeds. It's about 70 millimeters per second. You see, we perform some basic motions and try to see the behavior of our axis. Yeah, obviously interpolation. These are actually not accelerated videos. They are 1x. Yeah, this is a real-time video, but later I will show you some manufacturing videos. They are not real-time. This one is real-time. We call it in real-time, and you'll see the real-time video. And this is the W axis. Yes, let me give you some brief information about the linear axis. We have 4 of them. First 2 have a resolution of 3 micrometers, and their maximum velocity is a bit higher than the other axis. It's 70 millimeters per second. And if you consider the vertical ones, they have a better resolution, but their speed is not that much, since we don't need high speeds in the vertical axis. if you consider the machining and the additive manufacturing operations, we don't need to have high speeds in the vertical motion. And these are the ranges of the axis. We have the largest range for the X1, and it's the same for the X, Y, and Y, Z, and W axis, which is around 400 millimeters. But obviously, if you use a 5-axis system, if you have B and C axis, you cannot completely use this whole range. Otherwise, you may have some pollutions with the part with other parts of the system. Our working volume is a bit less than these numbers. And here you see the just manufactured rotary axis, B and C. This one is C, this one is B, and all the parts of the interior, the mechanical parts are the same. The only difference is the adaptive parts on this top side, but the rest is the same. So we use the same technical drawings, same equipment. So they are replaceable. Their stepper motors are the same, and here you see the initial tests on these rotary axes. And these are the main properties of the rotary axis. We have 3 of them, B, C, and Q. As I mentioned, Q is related with the rotation of the extruder, and as you see, it has a bit worse resolution than the B and C axis. It's actually 200 arc seconds, but it's much less on the B and C axis, which is 60 arc seconds. And their maximum velocities are a bit higher compared to the Q axis. In the Q axis, we don't need to have that much resolution or that much speed. We will be rotating the extruder head very slowly, so that's why we designed accordingly. And the range of these rotary axes are 360. And in addition to these axes, we have some auxiliary units, and I didn't mention that we have 2 controllers in our system. In our electronic board, we have one controller for the motion control, X, Y, Z, B, and C, and we have another controller for the control of these auxiliary units. What are they? We have spindle, we have chip allocation system, and the extruder head. For the spindle, we use a very simple one, not a very actually professional spindle. As you see, its speed is not that much, up to 2,000 revolutions per minute power, and we directly control it by modulating the AC. And on the chip allocation system, we use a simple vacuum pump. Its power is 750 watts. And on the extruder head, we use an available extruder head, and it's the extruder head of actually Altimaker 3 type of 3D printer. We have done some hacking operation, and now we can easily use the extruder head of Altimaker. And in that extruder head, you may have 2 different print cores. This gives you lots of flexibility. You can print different materials. You can have different nozzles. So it gives you high flexibility. And since we are controlling the extrude head separately, you can easily control the fans, the lab, the temperatures of the nozzle. And furthermore, we have capacitive sensors on the extrude head. We can have some information about the leveling of our bed and try to level it properly. And then if there's something wrong, we will have a compensation type of algorithms, and the quality of the print, the quality of the manufacturing will be improved. And let me move on to one of the main novelties of this project. It's about variable bead width. What is that? Actually, we have a special nozzle, and as you see, the conventional nozzles have a circular cross section, circular opening, but now in our nozzle we have a rectangular orifice, and that's why actually we need to use a Q axis. With the help of Q axis, we are rotating this nozzle, and this vessel actually this help us have a larger bead or a smaller one. As you see in this configuration, this is the size of the bead, but once you rotate it about 90 degrees, your bead will be decreased. And according to design, we have a ratio 1:4, but in the experiments, we have the ratio 1:3, since as you see, the temperature is high, the material flattens, and we could obtain the ratio of 1:4, but at least we have right now 1:3. What is the advantage of it? So if you are, let's say, want to produce your part in a shorter time, we can switch to this mode and print it in a shorter time. But for the high detail regions, you need to rotate your nozzle and try to have smaller features. So this gives you another flexibility in terms of the quality of your and in terms of printing time. Let me show you an example of this approach. By the way, this is a bit low quality since the size of the video was too much, and we try to decrease the size by compressing it. And I think this is not real time. We increase the speed a little bit. You can see how this Q-axis is working. In a moment, you will see the outcome. These are preliminary tests. We perform it many times and try to have different thicknesses for each motion. Another important thing is that you can see here the only moving axis is the C axis. For the second photo, for a near circle, our actually head, not the head, but the table moves in x-axis, and then the rest is actually completed by the c-axis. And as you see, all the other axes are stationary, just the rotary axis is moving. And we are repeating it for some time to have some thickness. This is another, as I said, novelty of the project. You can have your prints in a shorter time, or you can have high quality prints. This is up to you. You can continuously change another thing. You can continuously change the width of the extruded beads in your, let's say, printing operation. Let me show you some videos about the basic printing operation. This is a time-lapse video. And since we are using the extrude head of the altimeter printers, we can do what they are doing. Actually, we have two nozzles. We can have water-soluble filaments. We can have different colors. We can set the temperature to different levels. It doesn't matter. This gives us high flexibility. Another one here. So we can use our system just like your desktop 3D printers. This is machine side. This is another, actually not real time. We increase the speed of the video. And in our initial test, we didn't want to do the machine or other operations at high speeds. To be on the safe side, we decrease the speeds and perform our manufacturing operation.
Chip verification system is working.
Yes, I forgot to mention about the details of the chip verification system. Here you see we have a nozzle here. The chip, the donated chips are evacuated through this pipe. It's connected to our vacuum pump. But we have little problems. Some of the chips are embedded into the part, but we need to actually develop some other methods to have high quality parts after the machine operation.
Also increases spindle speed.
Yes, we right now our spindle speed is not that much. It's around 2000 RPM, but we plan to increase it to 20,000 RPM. And once we do that, I think you will not have such problems. Oops. Last motion. So let me summarize the main properties and novel features. First of all, we have a flexible system. I mentioned many times that you can remove some of the axes, replace the heads. You don't need to have one extruded head or one milling head. You can have 2 milling heads, or you can have 2 extruded heads, depending on your project, depending on your applications. You can have such modifications. For instance, you can either change your vertical spinner to a horizontal one, or remove the machining side and just use our system as a 3D printer. And with such an approach, you can have a larger building volume instead of having a small one. You can have multi-axis 3D printer. Since we use Ultimaker print hat, extruded hat, you can have multiple colors, multiple materials at different temperatures. These are the same things I mentioned. Or if you're not happy with additive manufacturing, then you can use it just as a milling machine, 5-axis milling machine or 3-axis milling machine. It's up to you. And these modifications are not that difficult. You can do it just maybe in half an hour, in an hour. Furthermore, by having different hats, you can perform different manufacturing operations. It doesn't have to be machining operation. You can have other drawing or different manufacturing operations. So what we're planning to do in a few months, first of all, we want to have a more powerful spindle and more maximum speeds we want to have. And we want to change it to horizontal spindle configuration so that we will have less collision with the parts. In this configuration, we have some collision problems, but once it's made horizontal, I think most of our problems will be solved. Another thing we want to work on is the firmware of the B and C axis. We have little backlash and we have some limit cycle problems. With the help of a near and robust firmware, we will eliminate these problems. Another thing we want to work on is to decrease the number of controllers. As I mentioned, we have 2 controllers. One is responsible for the axis and the other one is responsible for the auxiliary units, but we want to have just a single one. And with the help of it, the communication will not be needed and it will be easy for us to handle all the cases, all the issues by using a single controller. And we want to also have a new system for the tool size determination. Actually, once you install a new tool, as you know, you need to do some measurements. But instead of doing that, we want to have an automated process. So you have embed such automated systems, hardware, and some little software into our overall platform. So in future, what we want to do in the upcoming year, first of all, we want to have a case like this one, maybe. Obviously, we will improve it so that the temperature will be controlled precisely and that will be a nice looking one. And we want to do more tests on our different parts of the system, on axis, on machining, on extrusion size. And also we want to have more test cases which are illustrating the capabilities of our platform. Not simple ones, but complicated ones so that we will convince some maybe future customers easily. We want to have, since we want to have, maybe we want to commercialize this product, maybe the second version. This is the prototype. And in the second version, we may establish a company maybe and try to commercialize our product. Another thing, right now we don't have a professional user interface. We are using some MATLAB and some scripts to obtain to actually manufacture parts, but this is in our agenda and we want a user-friendly interface. Another thing we want to do is to control the X and Y axis in a closed manner. Right now, we use stepper methods and we don't measure the position of our stages, let's say. With a simple addition of a sensor, we will be controlling them in a closed loop. And another thing we want to do is to try different materials. We'll even try some metals, aluminum, maybe some mild steel, some other polymers, brass. Yes, we have many possibilities to work on all these different materials. And we want to also make it easier for the users to send manufacturing data to the system. So we want to establish a Wi-Fi communication between the users and the machine. With the help of it, we may be able to remove our actually system from a different location. Let's summarize presentation. We try to actually design and manufacture a flexible hybrid manufacturing system. And with the help of this, we are combining actually the advantages of additive manufacturing and subtractive manufacturing operations. Since the main disadvantage of additive manufacturing is less surface quality and less low dimensional accuracy, with the help of machining, we can eliminate these problems and have much better products on a single platform. Another thing, this is a kind of a research platform for us. We want to work on various additive and subtractive manufacturing operations. And we want to work more on the generative design and path planning approaches. And as I mentioned briefly, we want to have a second version and try to commercialize this second version. Yes, that's all for me now. Professor, do you have anything to add? Thank you very much. Thank you. Okay, now I think we may have your questions, if you have any.
Yes, Dr. Yaman, thank you for your valuable presentation. And dear participants, you can use the question and answer section or use hands up option for asking any question. We are waiting for you. Yes, Dr. Hamid, please talk. Yeah.
Thank you. Thank you for the presentation. It was really good. I really enjoyed the presentation. I have a question regarding hybrid structures. For example, can we able to produce two different metals using the same technique? And the second question is, can we use the machining side and the additive side means interchangeably to create a geometry? For example, first we will create some geometry, then machining, and then we can continue additive and machining. I'm sorry, you might have told this, but I was not able to hear it properly because of sound problem. These are my two questions. Thank you.
Okay, let me start from the second one. We can do that. We can do little machining and then extrusion and then some machining or continuous machining. Then lastly, you may do some extrusion. This is possible. But for the first question, we actually designed our platform for mainly polymers. We don't actually, as you see, we don't have any lasers. We don't use any metal powders. But once you have kind of metal filaments, we may try, but always it will be very difficult for us to work with two metals at the same time. The thing we can do is that we may start with an aluminum block, do some machining, and then extrude some material on this aluminum block or mild steel block. So we may have plastics. Yeah, special plastics.
That's very good.
It's not designed mainly for metals.
So you can use multiple polymers as well. For example, multiple plastic as a hybrid tool, hybrid component.
Since we have interchangeable nozzles, if you have special nozzle for your specific polymer, you can just plug in and try to extrude that different plastics at the same time. As I mentioned, you can also remove the spindle from here and then put another extruder so that there will be two extruder heads. One may be printing ABS, other one might be printing ECG. So it's up to you.
Okay, so one last thing. You can do multiple things in the machine as well. For example, additive, producing different material and machining side by side.
Yeah, you can do that.
Okay, thank you. That's it. Thank you very much.
Okay, thank you, Dr. Hamay. Any other question? We are waiting. Okay, maybe we're going to have any question after Professor Yusuf Kaynak's speech. Before we finish the webinar, I would like to present Professor Yusuf Kaynak. He is the president of the Turkish Additive Manufacturing Association. We called it TAMA. Okay, Professor, we are listening to you.
Yeah, thank you, Dr. Yilmaz, for your introduction. Actually, I would like to also thank to Dr. Yaman for his great presentation, and also I would like to thank all the participants attended this webinar. Actually, as you know, last year we organized AMC Turkey conference, and this year again we were planning to do that, but unfortunately due to the well-known reason, the COVID situation, and we postponed that conference and replaced with actually, let's say, the TAMA Additive Days. We thought that we need to still communicate with the additive manufacturing society and keep in touch with them, and they exchange our knowledge and experience, and they also listen their experience, you know. And so this is the dynamic industry and the area, and so that's why we are organizing this seminar series. It's starting today with the presentation of the Dr. Yaman, and a great presentation, and we will end the end of this year. Actually, each year we will have a two presentation from the university as well as from the industry, and the experience. Actually, the researchers, engineers, and academicians will present their recent, actually, the experience and the recent the know-how, let's say. So we hope that it will be very useful and beneficial for the both side, and mutual benefit people attending and the participant will obtain. And also one more note, probably Dr. Yaman and Dr. Yilmaz already informed you, but as a TAMA, Turkish Additive, actually the Additive Manufacturing Association, we are just recently started to accepting the actually membership. We will have two different membership. One is the full membership, the another one is the associate membership. And you most likely receive the invitation email from the TAMA, and if you don't receive it, you don't need to worry about that. You can just go to the website of the TAMA and you can click on the membership registration, and you can apply to be the member, and hope that you will get some benefit when you become a member, and you will easily reach the recent advance of the actually the additive manufacturing society in Turkey as well as in the world. And again, thank you so much for attending. Actually, thank you all for attending this webinar. And also, I would like to again one more time thank to all the organizer and my friends and professor. And so I think today we're done, and we are expecting to attend the upcoming actually webinar. I think tomorrow, and again we have a next week, right, Dr. Yilmaz? So we will keep actually communicating with you and sharing the ongoing research in this area.
Okay, thank you, Professor. Before we close, is there any question right now to Dr. Yaman? I think there is no. Yes, Dr. Yaman, do you want to add something else?
No, that's all I think. If they have any questions, they can later write me on LinkedIn or send me an email. I can always answer the questions.
Thank you again. And dear participants, please follow TAMA from LinkedIn, social media, and our website for previous webinars. And don't forget to being a member of this community. And thank you again for your attendance. Thank you, Dr. Yaman, and thank you, Professor. And see you next webinar.
Next webinar is on Thursday. It's about design for additive manufacturing, but it will be in Turkish. And you can click on the registration link on our, again, LinkedIn page, and see you on Thursday.
See you.